Before starting today's session, let me ask a question. Do you mind if I move our session back to the eight o'clock Tuesday next week?
I think, yeah, I think that should be okay.
It should be okay, right?
Mhm.
Yeah. There's some kind of like a schedule. I mean, now it's just schedule will continuously just change every week. But I want to just pin down this session 8 o'clock. Because I was able to actually move the one another actual session to the Wednesday, so I can just move it back down to the 8 o'clock from 8:30. So I'm gonna send you the Zoom link for 8 o'clock next Tuesday, so we can stay with that schedule. Okay. All right. So we started like a DC circuit topic from the last session. And as I already told you last week, I'm going to just walk through some example problems so it help you understand how to use the basic formula we went through the last week. So basically, for DC circuit analysis, you need the um, basic rule. I mean, basic law is Kirchhoff law. There are two backbones of this law: junction rule and loop rule. So the sample problems will definitely just guide you how to use those rules to find out the values of individual component in the DC circuit. So let me give you the very first standard, circuit problem, and then I'll just get you the various different kinds of circuit, configurations with a different combination of parallel and series connections. And we'll just navigate the direction to find that the values of individual component in the DC circuits. Okay.
Yeah.
So let me draw this. Hold on. So
Oh,
what's
I
up?
also got my test back today for
Mm-hmm.
circuit test, or not
Mm-hmm.
circuit, my capacitance test. So
Mm-hmm.
today, last week we took a capacitance test. This week we took a quiz actually earlier today
Mm-hmm.
about resistance.
Mm-hmm.
It was just parallel and series resistors.
Mm-hmm.
And that's something you covered last session, so I think I was okay with that. But the capacitance test, I scored the highest I ever did on my test for the MC, but
Mm-hmm.
I think I failed the FRQ. The FRQ was a little bit difficult because I just made some like silly mistakes, but those were my
What
result.
kind of mistake are you referring to?
So
Like
for yeah,
miscalculation of different in the wrong number plug
no,
into the
it
formula?
was yeah, it was like a conceptual. So they gave me
Okay.
like a sphere and they gave me it was basically a regular capacitor, just like a
Uh-huh.
spherical capacitor essentially.
Uh-huh. Uh-huh.
But I accidentally misinterpreted it into two different capacitors. So when I
Mm-hmm.
used Gaussian's that law in order
Mm-hmm.
to derive like an equation,
Mm-hmm.
I had two different integrals and it's just one
Mm-hmm.
different integral. So I
Okay.
think I should be able to like like correct the mistakes next time.
Did your teacher give you a solution for that um, out of quizzes, answers and solutions already, or you're waiting for feedback from the school?
She like corrected it, but we're not
Uh-huh.
allowed to take it home. So I have to,
Oh, okay.
yeah, I'm going to class tomorrow during after school to just look over and correct
Yeah,
it.
why don't you get that information and email to me? I'll take a look and get back to you next session, and maybe even I can just reply back with the correct way to solve the problem.
Okay, sounds
You can
good.
give me the something. Okay. You're saying that the capacitor part, right?
Yeah, I also messed up on the um there was a series and parallel
Uh-huh.
capacitors.
Uh-huh.
Majority I did correct, except one part I didn't do correct. It said find the total like energy in the
Mm-hmm.
system, and I was like,
Mm-hmm.
I calculated V,
Mm-hmm.
like
Mm-hmm.
potential, but my
Mm-hmm.
teacher said that was wrong. So I don't know
Okay.
what I did wrong there, but I have
Okay.
to correct it tomorrow. Yeah.
Yeah, send me the information as much as you remember, then I'll just take a look at it, and we'll just at least I can maybe get you something
Okay.
as part of the discussion. So, okay, then let's move on to the circuit part. So, the first problem, I can maybe draw some circuit configuration. So, that DC circuit has multiple. resistor connected in parallel and the series connection with the EMF, the battery. So they provide current along this DC circuit, and then each resistor defined with a different value. So the first resistor has 10 ohm, second resistor R2 middle of the circuit has 25 ohm, and the third resistor actually connected with the fourth resistor in series, and that has 30 ohm, and fourth resistor has 10 ohm. So this the battery EMF provide that the 20 volt cross this DC circuit, and obviously that produce that current, first current I1 along this first line of this resistor. That split into the two direction, I2 along the R2 and I3 along the R3. So now the question is, we need to determine the power dissipated by R2 and R3 in this circuit. So you see that this R2. Let me change the color. So as you can see, if you look at the fraction of this DC circuit, this R3 and R4, as you can see, they are connected in series. But those two registers actually connected to R2 in parallel, and they are also those the three registers are connected with the first resistor R1 in series. So we have very carefully deal with the equivalent resistor out of these multiple connections of multiple resistors. So first step is figure out the equivalent resistor along this current passes. So for current path I3, as I said, R3 and R4, they are connected to each other in series. So total, you can think of this effective resistors R prime. So R prime out of those two resistors is R, obviously R3 plus R4. That's easy because that's a rule of resistor in series connection. And number two, now you look at R prime and R2. So if you redraw this picture, then it should be like this. There's R2 and there's R prime. Okay, you can just kind of redraw this part of circuit connection with this kind of modified configuration, but they effectively the same. Like R prime consists of R3 and R4. So now if you think of this whole thing, R2 and R prime, they're connected in parallel. So you can think of total effective resistor out of these two resistors is R double prime. So based on the resistor rule, the effective resistor in parallel should have this relations. So R double prime is same as one of R2 plus one of R prime. Because as I said, this two resistors, they are connected in parallel. So in case that the two resistors connected in parallel, they have this kind of relationship as I already showed you before. So from that, you can easily derive formula of R double prime in terms of R prime and R2, which is R prime times R2 over R prime plus R2. Okay, that is second part of this circuit, which is R double prime. Now that R double prime, as you can see, are connected with the R1 too, along the current path of I1, right? So number 3, if you just also draw the modified configuration out of this original circuit design, then that should be like this. This is R1, and there's effective resistor out of this 3, R2, R3, R4, which is R double prime, right? And there's battery connected to those two resistors. So you can think of this DC circuit only with the 2 resistors. One is given in the current path of the I1, and effective resistor out of R3, R2, R4, which is R double prime. So they are actually connected in series too. So you can think of whole total equivalent resistors are triple prime. So because these two resistor, they are connected in series, R triple prime is same as R1 plus R double prime, right? So now if you plug all the numbers into this formula, that is actually total. So now one step further, so you can even further simplify total circuit configuration into the only one with one effective resistor, which is equivalent to actually resistor for DC circuit. So then now this complex configuration of complicating the configuration of original design could be simplified into the only one battery and the one equivalent resistor R, which is REQ. So R triple prime is same as REQ. So if you plug the numbers out of these 4 resistors into this circuit, simplified version of this circuit, that is actually V, which is 20 volt. And we gotta just find out the value of REQ. So the R prime, let's plug that number. R3 is 30 ohm, and R4 is 10 ohm. So that is 40 ohm. So R prime is 40 ohm now. R double prime, you plug that number, 40 ohm times R2 is 25 ohm, middle of the circuit. And the denominator is 40 plus 25. So that is 15.4 ohm. And now you got to plug that into the R triple prime, which is equivalent resistor. So that just add the numbers into this formula. R1 is now 10 ohm, as you see in the circuit configuration, and now R double prime is 15.4 ohm. So that total equivalent resistor out of this simplified version of circuit configuration is 25.4 ohm, right? So now next step is to set up the loop. You can just set up any direction of a loop along this current path, but it's always easy to following that the mainstream of the current path. So now, as you can see, that the I1 goes along the I1 direction, right? So the clockwise. So you can choose that the direction of the loop one loop, and loop 1, same direction of current I1. So for loop 1, as I said, do you remember that basic junction rule and loop rule I just showed you last session? So if battery align the same direction of your loop, then battery always raise the potential and bring it up. And if your current path and the direction of the loop is same, then resistor always knock it down. So it comes with a negative sign. Okay, that's just a rule of thumb.
Wait, I was a little like confused because I was doing problems with like loops today.
Mhm.
And so isn't there like a conservation of energy where if you're in a battery, like there's no like changing of potential? Like why does it get knocked down?
Because you lose the energy by some sort of friction. That's a rule, role of resistor. So if you have some kind of current along the resistor, then actually that's lower that the potential, the I kind of like you have some kind of block and just lower the level of the potential bias. So while the current going through the resistor, it's there um, they're kind of like make that the current actually just going through that the reverse bias. Let me put this way. So like a resistor always actually behave in opposite direction of the battery, like electromagnetic source. So if you provide positive bias along uh, the battery, then the resistor player law actually to create a negative bias. It doesn't matter is the battery aligned the plus to the minus, minus to plus. Resistor always behave the opposite direction. Like, if you have the object in the flat surface, you drag that object, the surface, rough surface always create the frictional force, which create the energy loss, right? This resistor pretty much play this equivalent role of friction of rough surface. They always so the force you can think of this. We can put that this DC circuit image with this classical mechanical dynamics. You just produce a force by your two hands, right? You drag that the object in this direction. That is kind of same as the battery, okay? And it doesn't matter when if you just drag the object right hand side or left hand side, your friction always just act on opposite direction to the external force. Okay, so resistance itself plays exactly same role as the friction on the rough surface. So if the battery produce the positive current along the circuit, the resistor always produce the negative, actually just potential bias. So that's actually knock down the potential energy with respect to the battery.
Yeah, I think I was confused because like for capacitance, like
Mhm.
there is no potential energy lost in that. Like V stays the same when it's connected to a battery. Like there's no V is equal like there's a special formula for this where it's like V is equal to the epsilon minus IR
Mhm.
accounts for the knocking down because of changing to thermal energy, but that wasn't introduced in capacitance. I forgot about that.
Capacitor probably work a different way because they actually just store the energy by the biasing. There's no actual current flowing along the capacitor. There's
Yeah.
a displacement current, which is the kind of imaginary current, but that's not real. So when it has bias in both plate, that actually enhance that or lower that the effective potential, but there's no current along capacitor.
Yeah, but also like when you kind of have like a bunch of series and parallel resistors like this,
Mm-hmm.
so what I did, this was actually a check-in for today for
Mm-hmm.
series and parallel resistors.
Mm-hmm.
So I was able to find the total resistance uh,
Mm-hmm.
of everything. Like I did what you did, and I got like
Mm-hmm.
15 point. Was it 15 point? No, it's 25.4 is
Yeah,
a total.
25.44, right?
Yeah, so but then I used in order to kind of go backwards, I'd used V is equal to I times R, which is just like Ohm's law, V equals I times R. So I
Mhm.
did 25 point or I did 20 is equal to 25.4 4 times I in order to find that the current going through for the total thing. But the thing is, if you need to account for the drop down in energy due to
Mm.
these resistors, does Ohm's law like stay like uphold because you're just using V, you're not accounting for like V is equal to epsilon minus IR.
Um, so that like battery itself continuously provide that the potential, it can maintain that the potential along the circuit. So this is it has a consistent static actually current flow into the resistor. So that's I don't know if that's the answer for you, but that has the um, uh, so basically when you estimate that the total resistor out of the multiple component. Did you say that you assume that the ones the energy just lost that the register then it just that it's just gone? So that's confusing you or
No, it's more like what's confusing me is like Ohm's law, like V is equal to I times R, right?
yes, yeah.
Because like the V component, like but the potential, like say it's like the V is like from the battery.
Mm-hmm.
So wouldn't you have to do like there's no conservation of energy here because of the fact that like when you go through the resistors, there's a
Mm-hmm.
drop down in energy due to loss in thermal heat or thermal
Mm-hmm.
energy. So when you use like Ohm's law, V is equal to I times R, that V component, shouldn't it be like epsilon minus IR? Because you have to account for the fact that you're gonna lose some energy in the system.
You mean like this? P equal epsilon IR?
No, like epsilon, like the E, that like the what is it? The battery EMF.
Yeah, EMF.
Yeah,
Yes.
minus IR is equal
Yeah.
to E. That's like the whole thing that you were saying about like you're losing some of the potential because of
Mm-hmm.
like the resistors and the thermal heat. So
Mm-hmm.
when you do Ohm's law, wouldn't it be like EMF minus IR is equal to IR? Like you can't just use V because you know that in the system in the circuit you're gonna lose some like potential energy.
Well, that's you lose the energy out of the resistor, then the batteries that back it up. Just increase the energy once current. Like for example, you look at this simple, you know, DC circuit with the battery and the resistor, and then you just battery produce that current. That current flows that this the resistor, right? And that actually just um, based on the as you said the Ohm's law, that just the some of like a current actually just dissipated to the thermal energy and then they just lose the energy. But that's when that current comes back to this battery actually just make it up and increase that current, actually make that constant flow along the circuit.
Yeah, that's what I thought, but then I did a homework problem today, where the answer was V is equal to EMF plus IR. So you're not making it up, you're getting more potential. And I was confused because I always thought that like it would cancel out, like the battery would make it up, I guess.
I don't know. I have to just take a look. That's the basically that's what we have, like B equal IR, right? So right there's like whatever energy lost by the resistor is should be make up by this current. Sorry, this battery. So that's the basic rule.
Hmm.
So that's V equals IR. That's the standard formula for the Ohm's law.
Wait, maybe I'm thinking of it wrong. Let me look at the question really quickly. But um Oh, it says
Um,
oh yeah, because maybe it's the wording of it that I'm getting confused. It says like a car battery with a 12 voltage EMF
mhm.
and an internal resistance of 0.04.
But it has
Uh
internal register, right? Okay.
sorry?
It
Yeah.
has the internal register, so it's not ideal battery. It has internal register that create power loss too internally.
Oh, is that why there? Oh, because it says what is the potential difference V across the terminals? I thought that it would just be like the V is like what they give you. They give you 12 voltage for the battery, but because it specifies that there's an internal resistance, then it's gonna
Mhm.
change the
Yeah, that's actually continuously energy, additional energy loss through the battery itself. Battery also produce that, um, the power loss if it has impedance or resistor.
so it's not the same as like this situation.
Not different because now what I show you here is ideal battery. There's no internal loss, but if it has, I guess, what happening with that the circumstance, the as times goes, battery continues to lose the power, and that's what's really happening in the car. If you just use the battery for a long time, they start losing the power because it has continuous energy loss by internal resistor. But what I show you here is the ideal resistor. There's no internal, resistor. This battery itself is just continuously produce the whatever energy lost by the external resistor. So there's like complete loop. So they provide that the energy back to the resistor and make up the energy, whatever energy resistor actually, spent along the DC circuit. So ideally, that's when the current comes back to the battery. That's bring it up to the potential. I mean, the current level which provide to the resistor. But if the battery itself has internal, maybe like internal loss R, as time goes, that continuously lower that the potential because that produce additional energy loss. So that's like a little bit different situation than what I show you in the ideal case.
Okay,
So
that makes
in order to actually take into account, you got to just actually add that into your circuit equation because that, well, if you do that, yeah, some integral of your charge in time, that will actually end up with the exponential decaying function. And when time goes, then that reduced actually the power out of this battery because of the internal actually resistor. So that's what really happening in the real battery in the real world, and just and whatever what you see in this simple circuit is based on the ideal conditions, the resistor and battery, and even like wire itself also has actually resistor and resistance too. So if you actually just send the current along the wire itself also consume the some amount of energy, and also like current actually lost through the circuit wire too. Okay, so circuit has internal actual resistor, a battery has internal resistor, and they actually spend time, energy to make up that the thermal energy. So then a lot of energy actually lost to thermal dissipation as time goes. So that's maybe like what you are seeing in your problem. Maybe that's the different than what you have now.
Mhm.
So, okay, does it make sense?
Yeah. Mhm.
Okay. So let me see. So now, hold on. Let me just delete up some of that. So what we need to do is like find out current value so that we got the resistor total equivalent resistor out of the multiple element of sub registers So next step, as I said, we got to just apply the loop rule first along this loop 1, as I show you here. The total voltage out of the battery. And as I said, if the loop direction of loop is same as the current, then the voltage raise the potential, and the resistor actually lower potential. So you have to just add the minus sign with the resistor, and then also that's why you have I1 and R1 with the minus sign, and now the second part of that resistor comes with the current I2, so that's I2 times R2 equals 0. So as I showed you last session, that battery raised up the potential, and these two resistor in this closed loop here lower the potential by current times the resistor. So that is the first. So now from that, the I2 is V over I1 R1 over R2. So if you add that, so that now the current I1 is obviously V from the simplified version of the circuit. I1 is V over R equivalent. So the V is 20 volt, and the equivalent resistor out of this circuit is that is 25.4 ohm. So the current I1 from battery is 0.79 amps. So you got to plug that into this formula. Then the 20 volt minus 0.79 amps times R1 is 10 ohm divided by R2 is 25 ohm. So that is total is 0.48 amps. So now we find out how much current flows into R2, and last one is just apply the junction rule to find I3. This circuit current along the R3 and R4. Obviously, that's from junction rule is I1 is I2 plus I3, because that I was split into the R2 and the R3. So if you add that number, 0.79 amps for I1 and 0.48 for I2, then I3 should be 0.318. So you find the ratio of currents flowing along the R3 and R2. So now next step is find the power dissipation by these two resistors. So R2, so P2 is the power dissipation is I current squared times resistor. So it should be I2 times R2. So the I2 is 0.48 amps squared times R2 is 25 ohms. So that is 5.8 watts. So this amount of power dissipated by R2. Same thing, you just need to multiply I3, which is 0.31 amps squared times R3, that 30 R3 is 30 ohms. So that power dissipation by this resistor R3 is I3 squared times R3. So that is 0.31 amps. Oops. Okay, guys. Square plus R3 is 30 ohms, which is 2.9 watt. Okay, so that's actually, this is typical examples of DC circuit with the multiple resistors. You have to find the effective resistor step by step until you simplify DC circuit into this, the simple element with the battery and the resistor, then you make that the situation much easier to solve. So that is, yeah.
For the voltages, finding the individual voltages of like each resistor, instead of using like the junction rule, I kind of like used like a different way to find the individual voltages. So when I know the fundamental like Ohm's law, V equals I times R. So essentially what I did, I said 20 is equal to I multiplied by the total resistance. And then I was able to find that I component. Once I found the current, I know the current is going to be the same for R4 and same for yeah, same for R4, and the current is going to be the same for R3, 3,
Three?
2,
Which one? The same.
wait, I can't read the
Okay, let me clear up. In the circuit, which one? That's the R3 or R2? 25 ohm for R2, 30 ohm for R3. And you're saying that you use just the Ohm's law to individually actually just calculate potential per the resistor?
Yeah, because that's the way that my teacher taught me to use Ohm's law. Because you can do V is equal to I times R,
Yeah.
and once you know V is equal to 20,
Mhm.
equal to I times R total. So then you're able to find I. And then the two ones that are going to be in series are going to be R1 and R double prime, I think. And those ones are going to have the same I value. So then you can plug in V is equal to IR. You can plug in the R for R1, and then you can plug in the I from what you've previously calculated. You're able to find the voltage of R1. And then once you know the voltage of R1, then you can figure out you can also figure out the voltage for R double prime. They had the same I current. And then once you know the voltage, you know the voltage is going to be the same for all of the resistors in R double prime. So you kind of just like work backwards using Ohm's law.
Yeah, I mean, if there's no like a holy Bible to solve one, problem, there's not only like one absolute way to solve that problem. There's multiple different ways you can just apply. This is just one of just typical way to solve this kind of multi-connection DC circuit problems. So you can maybe just find the ratio of the current with respect to the resistor. Once you maybe find the R prime and R double prime, and then just directly apply power rule like I squared R to just estimate the power dissipation directly to that component. I mean, it just maybe it's faster to directly just calculate the current and then find the effective resistor when you actually just solve the problems in the real exam. That help you to save your time. But I'm saying that there's no absolute way or single way to solve that problems. As long as you just find that answer, that's fine. And that's based on this, solid the logics, then that's okay. But I'm just telling you what basic rule must possibly applicable to this kind of simple typical problem.